and a warm welcome to the AI with Arun Show. Have you ever looked up in the night sky and wondered what it takes to break free from Earth's gravity? For decades, that dream belonged only to giant governments and billionaire backed Western conglomerates. But today, that story is changing. In this episode, we are exploring a historic milestone that took place on the 18th of July 2026. We are diving into the story of Vikram, India's first privately developed orbital rocket. This is not just a story about machines, it's a story about how cutting edge AI, robotic assembly lines, and 3D printed rocket engines are democratizing space, making it faster, cheaper, and more accessible to the world than ever before. Every great revolution needs a pioneer. In India's private space sector, that pioneer is Skyroot Aerospace. Founded by visionary ex-ISRO scientists, Skyroot set out with a seemingly impossible goal to completely rewrite how rockets are built and launched. For over 50 years, India's space endeavors were exclusively led by its brilliant government space agency, ISRO. While ISRO achieved incredible things, government agencies naturally move with caution. Skyroot represents the spark of startup agility. They brought the fast-paced, fail-forward culture of Silicon Valley to the aerospace launchpad. By blending deep tech with lean operations, they have proven that a private startup can build orbital class technology from scratch. So how did they pull this off? It started as a step-by-step journey. In 2022, Skyroot made history by launching Vikram S, India's very first private suborbital rocket. Think of suborbital as dipping your toes in the ocean. You go up, touch space briefly, and come back down. But with Vikram 1, they launched right into the deep end. They achieved a full orbital launch. Getting into orbit is vastly harder. It requires achieving mind-boggling speeds of over 28,000 kilometers per hour to keep from falling back to Earth. To achieve this, Skyroot did not use old blueprint designs. They integrated deep tech, AI-driven manufacturing from day one. Their goal was not just to build a rocket, but to create an assembly lines that could roll out a launch-ready rocket in just 24 hours to serve global commercial clients. Let's transport ourselves to the launch pad on July 18th, 2026. The location is Sriharikota, a barrier island off the coast of India. The mission was named Agaman, a Sanskrit word that translates to arrival or advent. And what an arrival it was. As the countdown reached zero, Vikram 1 rose to life, lifting off into the morning sky. The goal was to deploy multiple miniaturized satellites into a precise orbit 450 kilometers above our heads in what we call the low Earth orbits, or LEO. The mission was the ultimate exam. It validated years of lab research under real extreme cosmic conditions. It proved that two major breakthroughs perfectly: an ultra lightweight frame made entirely of carbon fibers and a highly advanced 3D printed engine designed to guide the rocket through its final critical moments in space. Now let's look under the hood of Vikram 1. To understand its architecture, imagine a multi-stage relay race. Vikram 1 is a four-stage rocket. The first three stages are solid propulsion stages powered by Skyroot's Kalam series motors. Solid fuel is like a high-tech firecracker. Once you light it, it burns with a massive, unstoppable force to push the rocket through the thickest parts of our atmosphere. But the fourth and the final stage, sitting at the very top, is liquid fuel. This is the Raman engine cluster. Liquid fuel is like a kitchen sink tap. You can turn it on, turn it off, and adjust the flow precisely. This combination gives Vikram 1 the perfect blend: raw brute force at the bottom to escape Earth, and surgical and dial-in precision at the top to place satellites exactly where they need to go. Now, how do you build a robot or a rocket in the 21st century? You don't use hammers and manual welds. You use AI and robotics. Skyroot utilizes massive multi-axis robotic arms and spin and wind carbon fiber threads around a mold with microscopic precision. Because carbon fibers are incredibly strong but thin, any slight misalignment or human error could cause the rocket to rip apart under the immense pressure of launch. To prevent this, Skyroot uses AI optimization. Algorithms analyze the fiber's path and tension in real time, removing excess material and keeping the rocket incredibly light. Furthermore, they use what we call digital twins. Before a physical bolt is even turned, A highly detailed digital replica of the IM rocket is built in a virtual simulator. AI subjects this virtual rocket to thousands of simulated flights, predicting and fixing issues before they even happen in the physical world. If AI is the brain of the manufacturing process, then 3D printing is its hands. Let's talk about the Raman engine cluster that sits at the top stage of the rocket. Traditionally, rocket engines are unbelievably complex. They're made of hundreds of tiny individual parts, valves, pipes, and cooling jackets, all welded together. Every single weld is a potential point of failure. Skyroot bypassed this entirely by 3D printing their engines out of advanced metal alloys. Instead of assembling hundreds of components, a specialized 3D printer lays down microscopic layers of metal powder, fusing them a laser to grow the engine as a single solid piece of metal. This reduces the part count to virtually one, slashes manufacturing time from months to days, and dramatically reduces the risk of engine failure. We have talked about the brain and the engines. Now let's talk about the body of the rocket. In aerospace engineering, gravity is a relentless opponent. Every single gram of weight you add to the rocket's structure is a gram of weight you have to subtract from the satellites you want to carry. This brings us to a fundamental rule of rocketry. Weight is the enemy. To win this battle, Skyroot turned to advanced materials science, engineering, and all carbon structure. Now look at this number on your screen. 100%. Vikram 1 features an airframe and solid motor cases made entirely from carbon fiber composites. To understand how revolutionary this is, think of a vintage wooden tennis racket compared to a modern, ultra lightweight carbon fiber one. Carbon fiber is stronger than steel, yet it weighs a fraction of the amount. By replacing heavy metals like aluminum and steel with carbon composites, Skyroot achieved an incredibly high strength to weight ratio. This massive reduction in dead weight means the rocket requires less fuel to lift itself, leaving more energy to carry heavy, valuable commercial payloads into orbit. It's a masterclass in efficiency, making every launch significantly cheaper and commercially competitive on the global stage. Let's talk about the muscles. To get to space, you need raw, unfiltered power, and that comes from the Kalam solid booster series. The first stage is powered by Kalam 1200. This beast generates a staggering 120 tons of peak thrust to lift the rocket off the pad and punch through the thickest, most resistant layers of our atmosphere. Next is the Kalam 250, which takes over in the upper atmosphere. It features something called the flex nozzle thrust vector control. Think of this like holding a garden hose and tilting the nozzle to direct the water flow. By physically tilting the engine's exhaust, the rocket can steer itself dynamically in the vacuum of space. Finally, the Kalam 100 fires, providing high efficiency vacuum thrust to transition the vehicle into the edge of orbit. It's a perfectly synchronized sequence of power. While the Kalam boosters provides the raw physical muscle, the avionics provides the guiding mind. Inside the nose cone of the autonomous mission computer, this is the true pilot of the rocket. Once the rocket leaves the launch pad, human controllers on Earth cannot react fast enough to correct for sudden violent high altitude winds. The mission computer does this entirely on its own. Using sophisticated autopilot algorithms, the computer processes data from onboard sensors thousands of times per second. If a gust of wind pushes the rocket off course by even a fraction of a degree, the computer instantly calculates a correction and commands the Raman engine to pulse, keeping the trajectory absolutely perfect. Even better, the system is modular. It can be easily reprogrammed for entirely different missions in just days rather than months. Now that we understand how this incredible machine is built, guided, and fueled, let's talk about the actual job. A rocket, at the end of the day, is a delivery vehicle. Getting to space is only half the battle. The real victory lies in the precision deployment of payloads. Let's look at the satellite and complex processes that took place during the mission Agaman. Think of Vikram 1 as an Uber pool, but for outer space. It's a rideshare vehicle designed to carry multiple small satellites on a single launch, drastically lowers the cost for everyone. During mission Agaman, Vikram 1 carried a diverse suite of payloads. This included Scope, an advanced Earth observation satellite designed to monitor our planet. It also carried Solaris S3, a sophisticated scientific research payload. But perhaps the most exciting payload was Embrace, a tech demonstrator featuring a miniature robotic debris capture arm. As space gets more crowded, space junk is becoming a critical threat. This Indian developed robotic arm is testing how future space can catch and clean up space debris, proving that Vikram 1 isn't just launching satellites, but actively enabling a sustainable future for orbital operations. To appreciate how special Vikram 1 is, let's compare to its global peers on this table. Now, first, look at a Rocket Lab's Electron, the gold standard of private small satellite launchers. Electron is an incredible rocket, but it requires a significantly higher budget and longer turnaround times. Now, look at India's state built SSLV by ISRO. It can carry a slightly larger payload, but as a government rocket, its manufacturing cycle is bound by traditional processes. Vikram 1 bridges the gap beautifully. It matches them in payload and capacity of around 480 kgs, but wins on speed and materials. Because of its all carbon composite frame, 3D printed engine parts, and AI optimized manufacturing, Skyroot can build and customize this rocket at a fraction of the cost. Their target is a launch turnaround of under 24 hours. This means a client could call Skyroot and have the satellite in space the very next day. Why does all of this matter to the average citizen? Because space is no longer just about science fiction. It's a critical engine of the global economy. Now look at this growth projection. In 2023, India's space economy was valued at about $8 billion. By 2030, that is projected to grow to 45 billion. And by 2040, India has a vision of achieving a staggering $100 billion space economy. How do we get there? We can't do this with government launches alone. We need private enterprises. Satellites handle our GPS, our weather forecasting, agricultural monitoring, and global internet connectivity. By providing cheap, rapid access to space, rockets like Vikram 1 are the actual highways that will carry this multi-billion-dollar economic expansion into the future. The successful launch of Vikram 1 is not a final destination. It is simply the opening chapter of a much larger journey. If we look at Skyroot's roadmap, the successful flight in 2026 has unlocked the door. In 2027, they plan to transition into full commercial fleet operations and begin the development of Vikram 2, an even larger variant. By 2028, we will see the introduction of Vikram 3, designed to carry heavy payloads deep into orbit. And looking forward towards 2030 and beyond, Skyroot is aiming for the ultimate holy grail of aerospace, reusable launch vehicles or RLVs. Imagine an airplane that you had to throw away after every single flight. Traveling would be impossibly expensive. That is how rockets work today. By building reusable rockets, Skyroot will bring the cost of spaceflight down even further. As we begin to wrap up, let's reflect on what this truly represents. We are living through a profound historic shift. Space is no longer a restricted zone reserved for a select few. The successful launch of Vikram 1 is proof that the spirit of private entrepreneurship can reach the stars. It shows that a dedicated group of engineers using modern tools like AI, 3D printing, and carbon composites can build a world-class orbital rocket right out of a startup warehouse. Vikram 1 is just the beginning of a decentralized, democratized, and highly creative era of human space exploration. Thank you for watching. If you learned something, please consider joining us as a member. All you have to do is click join right below this video. And please like, share, and subscribe to the AI with Arun Show. I'll see you in the next video.